We're back in the Simpkins Physics Corner. Today, ladies and gentlemen, we're talking about graphs. We got position times graphs, velocity time graphs, acceleration time graphs, all the maths with all the graphs. Let's jump into it. See, ladies and gentlemen, I don't know how long it's going to take you, but let's ask the Sonic kid. When will you learn that your graphing has consequences? Because it does. And if you haven't seen that meme, go check him out, the Sonic kid. He's epic, all right? But here is the magic of what happens. When we make a graph of position versus time, the slope of that xt, or position versus time graph, gets us the velocity. Now the question here is why? Well, we know rise over run is slope, right? Well, what's the rise of the graph? X. What's the run of the graph? Time. And so rise over run is x over t. And x over t, by definition, displacement over time, is velocity. In the same way, this magical thing happens with velocity time, where if I take an initial and final velocity, and I take a change in velocity over time, that is the definition of acceleration. And so rise over run, or the slope of a VT graph, gets us acceleration. Mr. Simpkins, how do I remember that? Well, just ask yourself, what does the rise over run get me? Rise over run gets me change in velocity over time. Oh, I know that's called acceleration. What does the rise over run get me over here? Ah, displacement over time. That's the definition of velocity. So the first thing that we learned briefly in the last lesson is this idea of slope. But we can actually find even more things with graphs. So let's first start with the Derek Zoolander Center for Kids Who Can't Read Graphs. Good. We want to learn how to do other things good too. How far did the object end up away from its origin? The first thing you should always look at when you're seeing a graph for kinematics is it a position time, velocity time, acceleration time graph? Can't tell you how many students, either on my test or on the AP exam, which is a real rip, is they're like, oh, looks like a velocity time graph, but it's a position time graph, and it means a completely different thing. So the first thing you want to do is read the y-axis. Is a position time graph, and our initial position would be 0 meters. So we do all this jazz, we take all these steps, we go through this whole thing, but by the time we get to the end, what's our final position? Oh, still 0. So the question here, how far did the object end up away from its origin? That's asking how far are we from where we started and in what direction. And that is the definition of displacement, which is final position minus initial position. And that would be 0 because we didn't move anywhere. So the displacement was 0. Now, just a quick note. Remember we said that distance, everything counts, right? So let's just add up the distance that we covered here. From 0 to 60. So we covered 60 meters of distance. And then we were at rest because we didn't go anywhere. We are still at 60. Then we went from 60, we went all the way down to a position of negative 40. How far do I have to walk to do that? I have to walk 100 meters to do that. And so far, every step counts. I've walked 60 and I've walked 100. And then I go from negative 40 back to 0. That's walking another 40 meters. So if I add those all up, the distance would be, if you said 200, you're on the right path. So the distance is 200, the displacement is 0. That's because displacement is how far we are from where we started and in what direction, and distance is the total steps taken. Now, these aren't the only things that we can find from looking at our graph. If I erase some of this information and kind of clean things up a little bit, let's take a look at this idea of your actions having consequences or your graph having consequences. And in this case, we can find the velocity from the position time graph. So I briefly reviewed this skill in the last video. Let me show you some details as to how this works. All right. If I want to find the velocity from 0 to 10 seconds, here's 0 seconds, here's 10 seconds. All you would do is find the slope. So I could do some big fancy formula. I guess I'll show it to you once. M equals y2 minus y1 over x2 minus x1 for math class. That's the slope formula. Okay, but really we're just calculating rise over run. So our final y here was 60. Our initial y was 0. And our final x coordinate was 10. And our initial was 0. So this would be 10 comma 60 right here, and this would be 0 comma 0. So that's the data points that I just used for the slope formula. 60 over 10 gets us 6. What does that mean? That means the rise over run, the meters over the seconds, meters is rise, seconds is run, the velocity here is positive 6 meters per second. So the velocity for that first interval from 0 to 10 seconds is 6 meters per second. What's the velocity for the next one? Well, the slope is the speed, or in this case, the slope is the velocity, and the slope is 0 for those next 5 seconds. So it's pretty quick and easy to find out that the velocity is 0. Now, let's take a look. You can have negative velocity, of course, because velocity is speed and a direction. So let's take these points, all right? It looks like we have 15 comma 60, and over here we have a point of 30 comma 0. All right, so if I label those and do the slope formula, I can get real fancy, but basically we drop 60 and we move over 15. So our rise over run would be 60 over 15, but it's a drop. It's in the negative direction. And so 60 over 15, that would get us negative 4 meters per second. If you're wondering where the negative comes from, well, look at the slope formula. It's final minus initial, right? So it would be y final minus y initial over x final minus x initial. Sorry, I confused something here. Sorry. Y initial was 60. My bad. All right, so this is 60. That makes a lot more sense. So that one's 60, and that one's 30 minus 15. And that's where you get it. You get negative 60 over 15, which simplifies to negative 4. So taking the slope of a position time graph gets you velocity. Now, you notice the slope doesn't change, like, right? This is a steady slope all the way down, so I think it's pretty safe to say it's still negative 4 meters per second down there. Sorry about the streak there. And then, of course, this one we could just calculate its rise over run. So we rise 40, we run 15, and so whatever 40 over 15 is probably some decimal. That will be our slope for there, okay? So let's do that, 40 over 15. That's not what I wanted. There we go. 40 over 15. All right, 2.6. So our final velocity is 2.67 meters per second. All right, so that's the first thing, is that the slope of the position time graph gets you velocity, and that's why, okay? Now, if you feel like you're taking crazy pills, just wait till we see a velocity time graph. Oh, we can get so many things. We can find the displacement, how far you travel, by doing the bounded area of a velocity time graph. Now, why might that be? Well, remember, let's go back to our definitions. Rise over run. All right, that's slope. But what if I make a shape here and I label these sides? You see, these sides would be in units of meters per second, and these sides would be in units of second. And how do you find the area of a shape? Don't you do, in this case for a rectangle, length times width? Well, what would happen if you were to take the area? You would do length times width in this case. And what would the units be for that? It would be meters per second times seconds. Huh. What happens when you have a seconds in the top and seconds on the bottom of another term and they're multiplied together? Those seconds will annihilate, or they'll cancel each other out, and our answer will be in meters. Oh, meters measures displacement. All right, how far you are from where you started and in what direction. So in this case, because we're above the x-axis, we know we're moving forwards, that would be a positive displacement. Down here, if I were to calculate the area of this little triangle right here, that would be a negative displacement. Why? Because I'm in the negative velocity zone. I'm moving backwards, and if you're moving backwards, you're not going to end up ahead of where you started, right? So that's, well, we're going to unpack that here in just a second. The velocity, you literally just read the graph, okay? So if I say, what's the velocity here? You just go over and say, oh, 7.5, I guess. Well, according to the scale. Or I scribbled all over my scale. No, that's not right. 0, 5, 10. Dude, this scale is horrible. Who picks this scale? I can't see it, sorry, I gotta erase things. But yeah, easier said than done, Mr. Simpkins, right? Okay, so here we go. So if that's 5 and that's 10, we got 1, 2, 3, 4, 5 increments there. Each one's 2, so we're looking at 8. We're looking at 8. All right, so you just have to read the scale of the graph. Mr. Simpkins said it was easy, and it took him so long to do it, but you'd be 8 meters per second there, right? And then you drop down, you'd be 0 meters per second down here. Then down here, it looks like you'd be negative 4 meters per second riding it the rest of the way. So velocity, just read the graph, literally. Acceleration is slope, like we mentioned earlier. So the slope is the rise over run. So here we have a negative acceleration, right? And then, of course, the acceleration here would be 0. Why? Because the slope's 0. So if you wanted to calculate the acceleration of something from its velocity time graph, you would just do the change in velocity over time. Let's just take one quick look at what that would look like. All right, let's use this point right here because it's convenient. So x comma y, so 5 comma 0, and this one is 3 comma 8. All right, so if we do our slope formula, we would do the final velocity minus the initial velocity divided by the final time minus the initial time, and that would be negative 8 over 2, or negative 4, and our units for acceleration are meters per second squared, because it's going to be meters per second divided by seconds. So meters per second, or meters per second squared. That's acceleration from the slope of a VT graph. All right, you're not taking crazy pills, but you can find a lot of stuff from a VT graph. VT graphs are like the most treasure trove piece of information here, all right? Because a VT graph, I can read it, I can slope it, or I can bounded area it. So if I were to take the bounded area, just to define this for you guys, it's the area between the function that we see, the axis that we're talking about and the other bound of time. So in this case, we go from 0 to 5 seconds. We go from a velocity of 0 to a velocity of 6 meters per second. Sorry, my graph's a little rough here. But if I wanted to find out the displacement from 0 to 5 seconds, all I would have to do is find the area under the curve. That's the area. What shape is that, ladies and gentlemen? Ah, that's a triangle. 1/2 base times height for all you math geniuses out there. And so that'd be 1/2 the base. It looks like 5 seconds. The height is 6 meters per second. And that would be 30, and half of 30 would be 15. And since we're in the positive region of velocity, we are traveling positive 15 meters forwards. To do the acceleration, you do the slope. So here you would do 6 minus 0. That's the final velocity minus the initial velocity, divided by 5. And it'll get you some kind of fun decimal like 1.2 meters per second squared. So if you want to take a pause real quick and try out the other ones, check in with me. Not too bad to do that. All right, this one is a beast. All right, to find the displacement, so let's take a look. Indicate every time for which the cart is at rest. Remember what I said at the beginning of the video. What kind of graph are you looking at? That's going to matter. Because when are you at rest? When your velocity is 0. Where is your velocity 0? Right here and right here. So the answer to that is at 4 seconds and at 16, 17, 18 seconds. All right. A lot of people will be duped. They will say, well, a horizontal line means rest. Not on a velocity time graph, it doesn't. Okay. So on a velocity time graph, you just read the graph to get velocity. That's why we got the answer we did there. B, indicate every time interval which the speed is increasing. This will burn a lot of other people. Let's talk about what this graph shows. It shows a positive velocity, and then we get to 0 velocity. So if I was moving forward and then I'm not moving forward, I'm slowing down. But here's where people get burned. Mr. Simpkins, the graph is going down. What a terrible description. All right, let's be a little more specific. A better explanation would be, Mr. Simpkins, my velocity was 0, and now my velocity is -1. Well, let me ask you a question. Who's going faster? Someone moving 0 or someone moving -1? Answer, this person's going faster. So once you are in the negative velocity region of your velocity time graph, which is anywhere below the x-axis, why? Because all the values are negative. Once you're down there, you're moving backwards. And so this is actually speeding up backwards. So this would be one of your answers for part B. You would say from 4 to 9 seconds, we were increasing our speed. And then, of course, you would say from 18 to 20 seconds, you were increasing your speed. This is a speed decrease because you were going -0.4 and then you're going 0. -0.4 is faster than 0, so you are decreasing the magnitude of your speed. Let me take a quick pause so I make sure I fit the last 2 minutes. We're going to make it. So last one I want to do here for us today is part C. Determine the horizontal position of the cart at 9 seconds. So we got to go all the way to here. If the cart's located at x equals 2 meters at the initial position, because it doesn't show position on this graph, right? It had to tell us where we started. So how do you do that? This is a velocity graph, Mr. Simpkins. How am I supposed to figure out how far I went? Well, look at the giant orange box right there. To find the displacement, you do the bounded area. So for time's sake, just take a look at these triangles. If you go ahead and do the math, we go to 1, 2, 3, 4 seconds, and we have a height of 0.8. And if you multiply 0.8 times 4 and do 1/2 of that for the triangle, you get an area of 1.6 meters. The answer is positive because the values are positive above the x-axis on a velocity time graph. In a similar fashion, but with different numbers, you would calculate the area for this. So this side of the triangle is of the length of 5, and then the drop there is length of 1. 1 times 5, half of that's 2.5. And because it's negative velocities below the x-axis, that means you're moving backwards. So here's the question, all right? How far did we end up from where we started? Well, it says we started at 2 meters, so that's where that number comes from. And in the first 4 seconds, we moved forward 1.6 meters. And in the next 5 seconds, we move backwards 2.5 meters. So the answer to that question is our final position is 1.1 meters. So here's another example of how you can use a velocity time graph to inform you about your displacement or your position. To summarize everything, you definitely want to take some time with this slide, is position time graphs. If you read it, it tells you where you are. If you take the slope, it calculates the velocity because delta x over t equals v. The bounded area doesn't mean anything. Velocity time graph, if you read it, it tells you how fast and in what direction. The slope tells you the acceleration because a equals delta v over t. And if you do the bounded area, you get displacement. The only thing we're going to do with acceleration time graphs is this, because the slope of an AT graph is a jerk and the bounded area is just, no, just don't do it. So have fun, y'all.